Okay, so the next thing we're going to talk about is rates of change, and I'm not going to do the last example from the part before because usually we'd only do 2 and then I'd let you do the last one anyway. So I'll try and put up a solution for that for you guys to check online and see how you're going. Okay, but we're just going to move on to rates of change because I'm running out of time. Alright, so I said before that whenever we're looking at derivatives, we're always looking at the rate of change of something. For example, velocity is the rate of change of displacement. We're looking at how the displacement changes. Depends on how the velocity changes. Okay, and this is a similar kind of principle for anything when we've got any kind of change. So, when we've got a derivative, that's always telling us the rate at which something else is changing. So if you think of anything that changes, for example, one of the easiest ones is like water leaking out of a bucket. The rate at which that water leaks out of a bucket is the derivative of how much water is in the bucket and the amount of time that we've got. Okay, so in general, dy on dx or f dash of x, the derivative of y with respect to x gives the rate of change of y with respect to x. So when x is increasing and y is also increasing, our rate of change increases and dy on dx is positive. So that's when we've got an increasing slope. Conversely, when x is increasing but y is decreasing, dy on dx is negative, and that's when we have a downward slope. Rates are a quantity, okay, and thus are usually expressed as a ratio between 2 connected variables. For example, centimeters per second, milliliters per minute, dollars per hour, etc. The average rate of change between 2 points in a graph is represented by the chord connecting any of those 2 points. Okay, so here's our derivative here. So that's our average. Okay, and when we've got our limit as h approaches 0, that is our instantaneous. Okay, so where we've got limit, that tells us the rate of change at a particular point. Alright, so if we look at our first example, it says consider the function y equals 2 over x plus 1. A and b are points in the graph with values of 1 and 1 plus h respectively. So show that the chord and slope is given by this. Okay, so if we're looking at a, that's where x is equal to 1. Okay, so y would be equal to 2 over 1 plus 1, which is 2 over 2, which is equal to 1. B is equal to x is 1 plus h. So y is going to be 2 over 1 plus h plus 1, which is 2 over 2 plus h. Okay, so now if we're looking at our slope of our chord, that's our average rate of change. So we've got f ab is equal to f of b minus f of a over b minus a. So that's 2 over 2 plus h minus 2, 1 over, which is 1, over 2 plus h minus 2. So we then have 2 over 2 plus h minus, we want to make common denominators, so we want all of this over 2 plus h. So this is going to be 2 plus h over 2 plus h over h. We can then cancel out our 2's. We're left with negative h over 2 plus h over h. Our h's cancel, and we're left with negative 1 over 2 plus h. Okay, which is good. That's what our question wants us to find. The next part then says, explain how we can use this expression to find the slope of the tangent at A. So by finding our limit then as h approaches 0, we'd end up with negative 1/2, which is the slope of our tangent. I actually don't really like this next example too much, so I want to skip over it. You guys can have a go, but we're going to look at the next one. So, according to a psychologist, the ability of a person to understand spatial concept is given by this formula here, where t is the age in years. Find the rate of improvement in the ability to understand spatial concept when the person is 9 years old and 16 years old. So, if we're looking at the rate of improvement, that's the instantaneous rate at those times. So we have to find our derivative. Okay, and because we don't have, so we're looking at so we'll call it dA on dt, okay, which is like the same as dy on dx, except we've got an a and a t, not an x and a y. And we're looking at 1/3 times by t to the power of -2. No, sorry, t to the power of, not -2, t to the power of 1/2 of the square root. So our derivative is going to be 1/3 times by 1/2 t to the power of -1/2. So that's going to be 1/6 t to the power of -1/2. Okay, we're then going to find when t equals 9 and when t equals 16. Okay, so we can sub that in. We're going to have 1/6. I'm just going to change this into a square root of 9, so it's negative, it's on the bottom of the fraction, so it's going to be 1/6 times 3, which gives us 1/18. Okay, and similarly for 16, we're going to have 6 times 4, square root of 16, and that's going to be 1/24. Okay. And then the last part says, explain why dA on dt is greater than 0 for everything between 5 and 18, and comment on the results. So, if our psychologist says the ability of a person to understand spatial context is given by that in years, that means that their ability to understand spatial concepts is increasing. It's greater than 0 between those amounts. Okay, so we let our equation equal 0 and find our result. Okay, I think we'll leave that there for the moment. I did say we were going to do 4 lessons. I think we're just going to do 3. I'm just going to do 1 more on optimization, and that's going to be it. And I'll put up, I will put up these written examples a bit nicer and all set out properly so you guys can see them. I'll take some photos. Okay, all right.